Hi, everybody, and welcome to the History of Networking here at the Network Collective, where we get really interesting people that we all stand on the shoulders of today to tell us how the technologies that we use today came about. And today, we're joined by Radia Perlman. I probably don't even need to introduce Radia Perlman. No, I just don't. So actually, I want to jump to Donald real fast and see how he's going before we get to Radia and Jordan and make sure that everybody's okay. I know Donald was trying to take naps earlier.
I was. Didn't work too well. But, so I'm Donald, and I lead the FR routing project.
When he's not playing guitar.
Yeah, that.
Or trying to take naps, apparently. No,
and Jordan.
My name is Jordan Martin, co-founder of Network Collective. I work at a reseller for my day job. You can find me at BCJordo on Twitter or jordanmartin.net.
Great. All right, Radia, take it away. Tell us about Spanning Tree.
Okay. Well, first I have to start with, I was innocently doing layer 3 of that. What that means is sort of having these routers that forward packets from one link to another, doing routing protocols. And that's what layer 3's job is. Layer 2's job is supposed to just get messages from one computer to a neighbor computer who's on the same wire. So along came Ethernet with great fanfare. And everyone was like all excited about it and was thinking that this was the new way to do networking. And they should have called it Etherlink and not Ethernet because they confused the whole industry. So I looked at it and I said, oh my goodness, it has different properties than the other links. So I have to do little adjustments to the routing protocol in order to make it efficient with this new type of link with new types of properties. But, no big deal. It was little adjustments. But kind of to my annoyance, people were then building network stacks that had no layer 3. They were putting their applications directly on Ethernet. And so I tried to argue with them and say, no, you still have layer 3. And they said, oh, go away, Radia.
We're still having that argument today.
I just said it sounds really, really familiar.
Yeah.
That's really sad.
Right. So everyone was building applications on Ethernet. And I was saying, but you may want to talk from one Ethernet to another. And they said, our customers would never want to do that.
No.
Famous last words.
So I kind of gave up because I was used to sort of no one listening to me. So then years later, they had built really nice applications. And they were big heroes because their applications were good, but it would have been just as good had they done it correctly, which is on top of layer 3. But it's hard to explain that to people. So one day my manager came to me because, hey, their customers did want to talk beyond a single building because, Ethernet doesn't scale beyond a single building. So my manager said, oh, Radia, you do this sort of stuff. Invent some way that with a magic box, you can let people on one Ethernet talk to someone on the other. And it's like, hey, that's what I've been doing my whole career.
No, but not that way, Radia. The other way.
No, but you don't want two Ethernets talking to each other. That'll never happen.
You don't even want two computers talking to each other. No good. But at any rate, the constraint was that we were not allowed to tell the end nodes, hey, look, you made a mistake, put layer 3 back. And we were not, there was not a single spare bit in the Ethernet header. And there was a hard size limit to the size of an Ethernet thing. So you couldn't add any fields to it or anything. So with those constraints, they had already thought of, gee, why don't we just move packets around? But, listen promiscuously. And whenever the ether is free on the other side, or if it's a token ring, whenever it gets the token, you can forward the packets. So that was fine as long as there were no loops. So the implementers were saying, well, let's just tell the customers not to configure in any loops. My managers, on a Friday, late Friday, he said, hey, why don't you figure out some way that with no configuration whatsoever, these bridges figure out some loop-free subset of the topology to move packets around, and they break all the symmetries and all that. And he thought it was going to be hard. So for some reason, he said, he thought he was being funny, and he said, and while you're at it, just to make it even more challenging, make it scale as a constant. So the amount of memory and bandwidth necessary to run this thing should be a constant, no matter how many bridges and links there are in the world, which is crazy. Nothing is a constant. The best you can think for is here. It'll probably be n squared or something. So he was going to be on vacation the following week. And this was before people read email when they were on vacation or had cell phones or anything. So that night, I realized, oh my goodness, it's trivial. And furthermore, I can prove how it should work. It actually scales as a constant. I'd never seen anything like that. And, by the way, the reason it scales as a constant is that if you're running the spanning tree algorithm, you have to remember the best spanning tree message you've heard on each of your links. If you receive a spanning tree message on a link, you have to compare it with the one you have stored, and whichever one is better, and there's a trivial comparison, you keep the better one and you throw away the other one. And since a spanning tree message is around 50 bytes, it means that if you have 7 ports, it only takes 350 bytes to run the algorithm. So I was really excited about this.
As well you should be.
Yeah, it's cool,
Right. So I spent Monday and Tuesday writing the spec, and I did it in enough detail that when the implementers wound up implementing it, it only took them a couple months, and they didn't have to ask me a single question.
Wow. Oh, that's nice. That's really nice, right, Donald? That's what we need to get to right there.
So I spent Monday and Tuesday. I had the spec done. I had the algorithm designed and proven and all that. But my manager wasn't around, and I had to show off. And what else could I concentrate on before I could show off to my manager? But he was, who knows where, completely unreachable. So I spent the remainder of the week working on the poem, which...
2 days for the algorithm, 3 days for the poem.
Absolutely. So for the record, I spent more time on the poem than I did on the algorithm. Wow. Spec.
That's amazing. The spec was basically an afternoon. Like it did sound like it wasn't that long. I mean, you seemed like you had the idea pretty much after you had the conversation with your boss. You wrote the spec the following Monday and Tuesday, and then you just had to wait. That's hilarious.
Yes.
So I'm surprised, though, that you didn't write the spec over the weekend. I mean, that's what we would do today. We'd have the spec ready by Monday, but, I guess Radia had her weekends back then.
Well, he also had young kids at the time.
Oh, well, yeah, that's true. That's true.
So at any rate, so then I worked on the poem. I knew that I wanted it to be kind of a variant of Joyce Kilmer's Tree poem. But I couldn't quite remember it. I could only remember the first and the last stanza. So I went to the library, the digital library, and the librarian said, oh, yeah, that poem. And she remembered that it was by Joyce Kilmer. And so we looked up Joyce Kilmer. We didn't have the internet back then. These days it would be trivial to find the poem. And we looked everywhere we could think of, and the only thing we could do was some, biography of Joyce Kilmer that was one paragraph long that said that he was known mainly for this one poem, which they didn't actually quote.
Wow, that's useful.
His poetry was beginning to show improvement, but then he got killed in World War I. So then he was like, where did I find this poem? So I called my mother, who has a fantastic memory. And so I asked her, and she quoted it for me over the phone. And so that was how I found the poem.
Wow. So from the spec and the implementation, how did this spread? I mean, this started in one little corner at DEC, right? You were at DEC at the time, right? Working primarily on phase 4 or phase 5? Which one?
Well, I did 3, 4, and 5.
3, 4, and 5, but this was like phase 4 timeframe, right? Or is this before that?
Well, it was around 1983.
Okay. So phase 3, phase 4 timeframe, that's earlier than phase 5. I think phase 5 is later than that. So, so basically because DEC wanted this problem solved, they started producing these boxes. Or, how did this become more common than just, at DEC or at DEC equipment?
Well, actually, so there was the spanning tree algorithm, and but the implementers wanted to implement the simplest possible device. And as simple as the spanning tree algorithm is, it still made their device more complicated. What they wanted to do was to tell the customers, just don't put loops in, which it isn't just because customers are confused and do the wrong things. It's nice to have backup paths in case anything fails.
Right. Yeah, of course.
So, but I actually sympathized with them because I thought of the whole transparent bridge stuff as a horrendous kludge to fix a mistake that the industry had made, which was leaving layer 3 out. And once every...
Wow.
So, it was... I didn't think it was the right thing to do, but it was only going to last for about 6 months until people had a chance to.
Wow. Yeah, I've heard this story before someplace.
Right. But then, so I didn't want to argue with them. About whether they should put the spanning tree in, because I figured they would think I was biased anyway. Once you write a poem, you really want to see the thing implemented.
You spend 3 days writing a poem.
Right. So I let management sort it out. And so management told them they had to implement it. Now, this was actually a really cool story as well, because I heard after the fact, the very first bridge sold was to an incredibly sophisticated networking customer, probably the most sophisticated networking company at that point. And so I heard the story afterwards that the sales guy went and told them, you have 2 Ethernets, you want to talk across them, buy this magic thing. And they said, but we're doing all these complicated networking things. Look at all these different protocols we're implementing. And the sales guy said, it's just going to work. And they said, no, we have to talk to the engineers. And the sales guy said, no, it's just going to work. So the world's most sophisticated customer had the world's simplest topology, which was 2 Ethernets and 1 bridge. They plugged it together. And it did not work. And there were so when field service came to figure out what the problem was, they realized and this is so much better done as a picture, but oh well. What that customer had done was plugged both ports of the bridge into the same Ethernet. So everything was working perfectly. There were no loops or anything. I'm really glad I thought of that case. And it just was, the spanning tree said, well, gee, I don't need to forward packets. If I ever do, I will.
Wow. So this must have been it must have been a government customer or something like that. I was expecting you to say it was Cisco or something.
Well, Cisco, I don't even think existed at that point.
Wow. Yeah, I was in 1983. I was probably still just starting to work on Cabletron boxes or something like that. It might have been pre-Cabletron. I don't remember. But yeah, that's a long time ago. Wow. So, well, cool. I mean, is there any other interesting stuff around spanning tree that you can think of? I mean, now that we've done all this other stuff, Radia, I mean, you've got to be proud of this little baby of yours that's gone out there and become like, what is it, like multi-spanning tree and EVPNs and all this other great stuff. Because we continue to refuse to use layer 3. I don't know.
Right. Well, that's kind of another long story, which is that if you ask networking experts, why do we have both Ethernet and IP, they'll confidently tell you because IP is layer 3 and Ethernet is layer 2. And I claim that Ethernet stopped being layer 2 once it stopped being CSMA-CD and became spanning tree. So because it's forwarded, it is a layer 3 protocol. It may not be the best routing protocol in terms of being confined to a spanning tree, which was necessary because of the constraints at the time. So the real question is, why do we have 2 layer 3 protocols? So an interesting question is, why can't we just hook everything together with Ethernet? Because the address is bigger than IPv4. Why don't we get rid of IP and just take everything together with Ethernet addresses? And the answer is, well, they're flat addresses, which is really convenient for lots of little networks, but not for organizing the entire internet. So then the question is, well, why don't we get rid of Ethernet and just hook everything together with routers?
With IP. Oh, wow. There's an idea.
And this is an extremely subtle thing, which is that IP has an idiosyncrasy that every link has to have its own block of addresses. So if you move from one side of a router to another, your address has to change. And routers have to be configured with which blocks of addresses are on which ports. You better get them right and so forth. IP, people do want to have a cloud with a flat address space. And so Ethernet looks to IP like a cloud with a flat address space. But that's an extremely kludgy way to do it. There was a competitor to IP done by ISO, which was called CLNP, Connectionless Network Layer Protocol or something, that had 20 byte addresses. And what was cool about it was not only that the addresses were bigger, but the top 14 bytes got you to a cloud, not to a single link. And everything in the cloud shared the same 14-byte prefix. So once you got to the cloud, routing was based on the bottom part of the address. So this is, in one sense, you can think of it as carrying IP and Ethernet in the same address, so you wouldn't have to do ARP. But it's even better than that because it was a genuine layer 3 protocol inside the cloud. But because we didn't do that, in 1992, people made what I claim is the single worst decision in the history of mankind.
You mean other than the invention of Ethernet? No.
Well, the Ethernet was okay as long as you knew what to use it for. Spanning tree is like so fragile, and it was fine as a quick hack until people fixed the endnotes. But given that they decided to go with IP rather than CLNP, they kind of needed it in order to create this illusion of a flat address space to IP. In 92, people said, hey, IP addresses, too small, need bigger addresses. Hey, look, here's a format that has 20 byte addresses. All the vendors have implemented it. Someone showed in just a couple months how he could port TCP to work on top of it. And then all of the internet applications worked immediately. And back then in 92, the internet was just this small researchy thing. And if it weren't kind of for the hysteria of, people that didn't even know what CLNP was, it was just done by a, different, not wanting to give ISO the satisfaction to say that anything they did was any good. If it hadn't been for that resistance, they could have snapped their fingers and we would have been using 20 byte addresses since 92.
But instead, we did V6.
Right, which we're still designing.
Well, it finally became an internet standard last week with 8200. And it's pretty humorous because the changes are still continuing and there's still argument over how to do neighbor discovery and how to do DNS discovery and all this stuff. And like you said, a lot of that would have been solved. Just use CLNP, be done with it. I mean,
Absolutely.
Or at least the addressing space, right?
Right. And you might think that, well, with this many more years of designing IPv6, it must be astonishingly brilliant compared to CLNP, because they could have learned everything from CLNP and then done other things. But it's actually technically not as good because it doesn't have the idea of a true layer 3 as the bottom level to be able to do a cloud. IPv6, just like IPv4, every side of every router has to have its own unique block of addresses.
So what's interesting is that there was an idea of having site local originally in V6, but that's been deprecated. And that's almost what they were trying to get to, it seems like, was a site local address where everything within the site would have the same address and you could just route to the site, which would be like your cloud. But then you would still have longer prefixes. You'd still have subnets in order to get to the host within that cloud. But then again, if you put everything in the network and put it all on the same /64 or thereabouts and just use the MAC addresses, the Ethernet addresses as your final part, but then you wouldn't get routing, right? You wouldn't actually get routing. You would actually still have switching at that point.
You do auto configuration with IPv6 by using your Ethernet address in the bottom part, but that doesn't, as you said, give you the actual routing. And besides that, IPv6 is sort of very much, they don't want to make decisions. So you could do it with DHCP, or you could do it by putting that in, or you could do something else. Researchers might think of something wonderful in the future.
Yes, I know, because I'm writing an IPv6 router requirements draft and everybody keeps telling me no Slack must be supported, no RDDNS must be supported, no ND must be supported. And you go through all these options, and then there's entire 20-page documents on all the different interactions between the bits in router discovery, neighbor discovery, in Slack and DHCP. And if you do this bit this way, it causes that to happen and causes that address to be there. And you're like, I needed 20 pages to tell me this. Maybe there should be a simpler way.
Right, because we were living with IPv4 for so long, things got invented like DHCP. And then people came to love it. And indeed, being able to hand out addresses, if you kept your MAC address wherever you went, people would worry about privacy. So we could have gotten by with only 3 bytes or 4 bytes as the bottom part if we handed out addresses with DHCP, which seems very sensible for a lot of reasons, to have kind of temporary addresses so it's not obvious, just for privacy reasons. And then people also invented NATs and then came to love them. They were a clue first.
I'm going to take exception with that. I don't know very many people who love NAT.
Well, customers do, because at least it's perceived, and it's probably true, that it gives a level of security that unless your node initiates the connection, there's absolutely no way to reach it from outside.
Right.
Yeah. So there is some level of security in NAT, but the difficulty is that what we've gone with NAT is we've actually NAT was actually invented to do that problem on the PIX firewall. That was the original NAT box, was a PIX firewall, which unfortunately is now going to give me nightmares, because when I was in Cisco TAC, Cisco bought the Cisco PIX, the PIX firewall, and made routing protocols, backline TRT, work on it. And for many years, they wouldn't give me access to the code, and I had to work on it blind with no access to the code. I didn't know what the thing was doing. But then it became this whole address saving thing, right? Where now I'm going to use port level NAT instead of address level NAT, and that's just a disaster. I mean, address level NAT is actually technically okay if you're not having layering violations, right? If the applications aren't using IP addresses and storing IP addresses in the data part of the packet someplace, well, who cares what the IP address is end to end? I mean, it is what it is, and the packet gets there, and how do you care how it gets there? But when you do this port level stuff, things get really squirrely, really fast, and very difficult. So, that's kind of...
Yes, the address stuff. So my favorite example is FTP, where IP addresses are carried inside the packet, inside sort of the application as text strings.
Yes.
As text strings. And so if you had an address that one of the parts was 111 and you change it to 6, the packet is now 2 bytes longer. 2 bytes shorter. So the NAT has to remember, it has to go inside and fiddle with that. But then since TCP numbers bytes, the NAT box has to also remember that for this TCP connection, the byte numbering is off, and have to always sort of diddle that in both directions, on the AG as well as the other thing. And I have to admire the NAT people, because if I were to set out to try to do something, as soon as I hit, the first issue, and certainly by the time I got to NAT, I would have said, well, it was a cool idea, but it doesn't work. Let's drop it.
But they kept poking at it and pushing it and making it like, wow.
Right. So,
it might have been too late at that point, right? I mean, people were using it and go, we got to get this working now.
Right. Yeah, so when I try to explain networking to people, I say there's no way to understand how networks work today. It doesn't make any sense. And if you try to make it make sense to you, you're just going to get confused. The only way to understand it is to understand the history, all these various little kludges that had to be done. And then, kind of as a throwaway line, I'll say, well, when you look at how we got here, you can then appreciate that perhaps intelligent design is better than evolution.
So I'm going to take that past 30 seconds of clips, and that's going to be like the bumper for this show, because it's so true, right? To understand we have to understand where we came from. That's why this is so valuable. So I appreciate you saying that.
Yeah, it's really cool. Yeah. So, any other questions from folk? I don't know where we are.
We're about 30 minutes in. I just an observation. I think it's hilarious to hear that it's the same problems. It's solving solutions with ridiculous constraints. It's we have a good solution, but we're not going to use that because well, I don't know why we're not going to use that. We're just going to do this other thing, and it's no different today. The arguments between, whether or not, how far layer 3 should go and people's beliefs that layer 3 should be everything, it's the same arguments. And I mean, we're talking, 30 some odd years ago.
30 some odd years ago.
These same arguments, and they just don't go away. It's the same stuff.
Well, essentially spanning tree was designed to solve the original data center interconnect problem.
and now we block it and filter it so we can solve the data center interconnect problem. And unique spanning trees. I also think it's interesting. One of the other observations, and I think something gets missed a lot by engineers who may be just learning this recently, is that layer 2 is fundamentally solving the same problems that layer 3 routing protocols are. We need a loop-free path. We need to know how to get from A to B in a loop-free mechanism.
That's right.
We need to be able to find an alternative path when it's not available. I don't think people think about it that way. And essentially, it's a routing protocol, but just running at that Ethernet level.
Yeah.
Well, so again, when you say at layer 2, it isn't really layer 2. It's just a different layer 3. Layer 2 is just supposed to take layer 1 is supposed to show you how to signal a bit. Layer 2, given that it can signal bits, figures out a way to say this is the beginning of a packet, this is an end of a packet, this is a checksum. So as I said, Ethernet is not layer 2. At all.
And this is an amazing observation to me. I've never thought about it this way. And the reason why I say it's an amazing observation is because it's really hard to define layer 2. When you're learning networking today, it's really hard to define layer 2 because of this very problem. It's very layer 3 like,
right. Yeah. This is what, Jordan, why I don't teach the OSI model any longer, because we broke it long ago. Our networks don't follow the OSI model anymore. The RINA model, which was John Day's model, is actually much more effective because you're looking at what does this thing try to do and not like where is it supposed to operate in the network stack. And you're trying to understand like what Ethernet does today is there's this physical stuff, and then there's addressing, which is multiplexing. But that multiplexing is not necessarily a single hop anymore, like what it was originally designed to be. It's not a single broadcast domain with CSMA CD. It's like actually being carried on top of IP, on top of VXLAN, on top of IP, on top, using BGP as the routing protocol. And it's like this weird thing when you think about it, that you're actually pushing Ethernet on top of IP, which is on top of Ethernet. It's like this whole bizarre mess.
So one of the other things I was curious about coming into this is there's been a lot of I'll say lost love for spanning tree, right? Lots of people want to get rid of it, want to stop using it. I was kind of curious coming in and talking to Radia, like what would that, how does that feel to have this thing that you created kind of have law? But it kind of sounds like you didn't really like it from the beginning. It was required. You were proud of this thing you created, and you should have been. But you would have preferred we did it some other way all along. Is that correct?
Oh, that is correct. I mean, It is an incredibly elegant thing. But then when you keep tweaking it to try to make it have more and more functionality, it's fragile, and it was fine for what it was, but it wasn't intended to, hook the entire internet together. And
yeah. So it's interesting, Jordan, because we heard the same thing from Tony Lee about BGP last time we talked to him, right? When he was talking about BGP and how BGP has become this big kludge where everybody throws everything into BGP. And it's like, why are you doing that? Invent another protocol, right? This is crazy.
We heard the same thing about IPv6 too, right?
Yeah, it's the same thing with V6, right? It just seems to be this pattern in networking technology that you come up with this really elegant idea, and then people glom onto this really elegant idea, and then they start throwing stuff into it, and they're fragile ideas, and they kind of break the idea, the original concept, and they keep throwing stuff at this idea, and eventually it all just causes a major problem. And it's like, this is not as I would say, when you invent a technology, you don't get to determine who's going to use it for what. They just go out and use it for things you never imagined. And they're not going to use it to the limits of what you thought the limits were. They're going to use it to the point where they've gone way beyond those limits and they've made a complete mess of things before they're done with it. That's kind of my feeling.
How about you, Donald?
I don't have anything more.
All right,
cool. So, Radia, thanks for coming on, and we'll have you back on to talk about ISIS because that will be entertaining. It's one of my favorite protocols. You know, I'm using it in the data center now, and people think I'm crazy, but it is one of my favorite protocols, and it would be awesome to have you come on and talk about the origins of that. And you know, it might also be entertaining to come on and talk about the origins of cryptography. I think you know something about that, about the concepts of cryptography in computer networking and how that all started out as well, some of the different pieces of that. Because I know you did your dissertation on Byzantine failures. Now, right. We're not going to tell anybody what Byzantine failures are.
Okay.
We're gonna make them go look it up.
Time to go learn.
Yeah, that'll be entertaining. So, but thanks for coming on, Radia. And, you know, I'll probably see you at some point, and we'll catch you on the next show when we get you back on.
All right.
Okay. Thank you.
Thanks.
So the poem is called Algorithm because every algorithm should have an algorithm. And the poem is, I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity, a tree which must be sure to span so packets can reach every LAN. First, the root must be selected. By ID, it is elected. Least cost paths from root are traced. In the tree, these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree.